I'm a big fan of calculus, especially cool integrals. It just feels nice to see pi or e or phi or gamma emerging from the integral like a hidden gem. It is purely amazing. I love cool integrals, so I know the Feynman's technique. However, I never learned this technique in my math class. With Richard Feynman's own words in his book, Surely You Are Joking, Mr. Feynman, I had learned to do integrals by various methods shown in a book that my high school physics teacher, Mr. Bader, had given me. It showed how to differentiate parameters under the integral sign. It's a certain operation. It turns out that that's not taught very much in the universities. They don't emphasize it. But I caught on how to use that method, and I use that one damn too again and again. The book Richard Feynman mentioned is called Advanced Calculus, published in 1926, almost 100 years ago. It was written by an MIT mathematician named Frederick Woods. There's only one integral example using differentiation under the integral sign in the book. This one. This is the integral that gives this trick its most popular name, Feynman's technique. We will solve this integral at the end of the video after a few classic and easier ones. Before we start, I encourage you to grab a pen and a piece of paper to follow this video. Our first baby example is gamma function. Let's consider the integral. For all t greater than 0, this evaluates to 1 over t. Now, if we apply Feynman's technique and differentiate it with respect to t on both sides, we have the derivative equals negative 1 over t squared. We can keep taking derivatives with respect to t again and again, and the nth derivative looks like this. Here's the final step. By setting t equals 1, we obtain the classic gamma function representation. Notice that although when we take the derivative, we assume n is always an integer, but the integral representation doesn't require n to be an integer. It can be a non-integer or even a complex number. It's like kicking the ladder away once you reach the roof, or with an old Chinese saying, burn the bridge after crossing the river. The sinc function doesn't have an antiderivative that can be written using elementary functions. The standard way to solve this integral is to use contour integral from complex analysis. Let's try Feynman's technique. First, notice that this function is an even function, so we only need to evaluate the right-hand side, which is the famous Dirichlet integral. An immediate goal of the Feynman's technique is to eliminate the annoying denominator. We can define ht as the following. Our original integral is therefore 2 times h0. Now let's calculate h prime t. This integral can be solved using Euler's formula. We can split sin x to two terms. E to the power of ix minus e to the power of negative ix over 2I. Simplify ht prime, we have two complex integrals. Because for every alpha whose real part is greater than 0, the following integral evaluates to 1 over alpha. This means the two parts in the parentheses are respectively 1 over t minus I and 1 over t plus I. Because our integral is a real integral, so the final results shouldn't contain an imaginary part. We are expecting some nice cancellations, and we have them. Therefore, ht prime becomes negative 1 over t squared plus 1. Because 1 over t squared plus 1 is the derivative of arctangent t, so we know ht equals c minus arctangent t, where c is a constant. To determine the value of c, we need to check ht's behavior when t goes to positive infinity. When t goes to infinity, ht goes to 0. Therefore, c is just pi over 2. ht equals pi over 2 minus arctangent t. Recall that our original integral is 2 times h0. Substitute 0, we see that I just equals pi. The next example is a classic Gaussian integral. This integral is connected to the normal distribution, so it appears everywhere. The standard trick to solve this integral is to square it, then reinterpret the double integral in polar coordinates, something everybody learns in the Calculus 2 course. You forget? I would recommend you to check out Brilliant, the sponsor of this video. You can find a variety of calculus courses on Brilliant, including ones that cover more advanced topics. Brilliant offers interactive lessons and challenging problem sets that can help you master this most important and useful subject. Beyond calculus, by signing up for Brilliant, you will not only improve your math skills but also gain problem-solving abilities that are valuable in many fields. As my audience, you can get a 30-day free trial and 20% off on an annual premium subscription by using the link in the pinned comment. Now, let's apply the Feynman's technique to the Gaussian integral. As before, we compute the right half of the integral and call it h. The key step is to create an artificial denominator such that 2 times h infinity is our original integral. We can perform a substitution to replace x over t with x. We pick up an extra t outside of the integral. At this moment, we can already deduce a useful result. The derivative of ht at 0 is pi over 2, by the definition. Taking derivative directly with respect to t is going to be ugly. We don't like the product rule and we don't like the denominator. So let's get rid of them by constructing this new expression. This new expression's derivative looks much nicer. Move the negative 2t times e to the power of t squared out of the integral. Then we can perform another substitution to replace tx with x, so we can cancel out the t outside of the integral sign. Look, we just reconstructed h infinity. The next step is the key step. When we perform the integration again, we pick up another h infinity. You see, with or without Feynman's technique, this integral is just easier in higher dimension. Something deeper is lurking here, but let's continue for now. Performing the integral, we obtain two terms on the left-hand side. The first term is just 0, and the second term can be computed using the limit we observed at the beginning. H derivative at 0 is pi over 2. Therefore, h infinity is square root of pi over 2, double it, we obtain our final result, square root of pi. It's beautiful and elegant. The challenge of Feynman's technique is to find out where the parameter should be, which often involves trial and error. Think about this 2005 Putnam question. Where should we put the parameter? There are at least two ways, and it's hard to tell which one is better. Let's try IA first. Take a derivative, everything seems fine. The right-hand side is obtained using partial fraction decomposition. These integrals are all elementary, so we can integrate them one by one. But look, when we try to reverse the differentiation, the first term has the exact form of I1, and the second term has exact form I0 if we treat A as x. The boxed part is already an equation, and I can bet you $2 that the remaining integral is 0. Feynman's technique overshot. It cancels everything and leaves nothing on the plate. Let's try IB. In this case, I0 is just 0, and we are interested in I1. Business as usual, take a derivative and perform the partial fraction decomposition. The integral part has 3 elementary integrals as well. They are pretty easy. When we integrate with respect to b, we pick up another I in the last term. So the two i's don't cancel each other now. The rest is piece of cake. Remember, this is a Putnam question. The Putnam computation is known for its difficulty. I found this example on Zaki's website. Check it out. He deserves more traffic. Zaki provided another solution, which primarily tries to eliminate the denominator directly. This is how it goes. Because of logarithm's nice property, we can construct a 1 plus x squared inside the logarithm in the numerator. Now everybody knows where should the parameter go. However, we have to complete the square in order to perform the integration with respect to x, and the integration with respect to t is even more tedious. I mean, it's still doable, but come on, I used Feynman's technique. I expect much nicer expressions. So I will stop here. Using Feynman's technique is like opening a box of chocolates. You can smell the chocolate to try to pick the best one, but you have to open and bite it to confirm your taste. At the end, let's go back to the origin, the exact problem in the 1926 Advanced Calculus book, from which Richard Feynman learned the technique. Okay, for simplicity, let's assume alpha's absolute value is greater than 1. Take derivative. It would be great if we can perform the half-angle substitution. First, extract 1 over alpha. Rewrite the integrand so x is only in the denominator. Let's extract even more alpha terms. To simplify our notation, let's call this part h alpha. Now let's perform the half-angle substitution. X equals 2 times arctangent mu, therefore dx equals 2d mu over 1 plus mu square. Still messy, but let's try to reorganize the alpha terms and group the mu square terms together. Look, we have two perfect squares, and we can simplify the integrand further so it looks like 1 over 1 plus something times mu square. Finally, we have our last substitution and pick up a pi in the numerator. It's time to go back to find the expression of I prime alpha. Substitute h alpha's expression, we find a lot of nice cancellations. Tastes great. We have I alpha equals 2 pi log absolute value of alpha plus c. But what is c? I can tell you the answer. C is 0. But we need to show that I1 is 0. This is the side quest of the question. Let's finish the quest. First, we construct 1 minus cosine x and apply the half-angle formula. Then we split the logarithm to get a constant part first. Split again. Oh, I love logarithm. Replace x over 2 by x. Now, in order to show I1 is 0, I need to show the boxed part is negative pi log 2 over 2. Let's continue the side quest. Replace x with pi over 2 minus x. We can replace sin x with cosine x. Therefore, we have this entity. Apply double angle formula. We pick up a constant term at the end. And finally, because sin x is symmetric on the interval 0 to pi with respect to the axis x equals pi over 2, the highlighted part becomes what we desired at the beginning, thus completes the proof. I hope this video gave you a good idea about Feynman's technique. Undergraduate calculus book doesn't include Feynman's technique because it's not trivial to justify the swap of integration and differentiation. The textbook has to cover more rigorous analysis content in order to introduce the Feynman's technique properly. I understand. That's why Richard Feynman got the book from a physics teacher, not a math teacher. But I truly believe sometimes doing without knowing whether it's allowed or possible is the most satisfying and fascinating experience in learning mathematics. What do you think?